Well, our topic of exposition is sedimentary basins and its mechanisms. Um, let's go to start talking about basins and its definitions. Perrodon defines a basin how a realms of subsidence with thicknesses of sediments commonly exceeding 1 kilometer that are today still preserved in a more or less coherent form. A basin is born from a methane of a sedimentary deposit and a more or less pronounced concavity in the basement. The basal deposits, which represent the start of a new sedimentary adventure, and generally mark a certain break with the past. The Earth's surface exhibits a wide variety of sedimentary basins, and their study reveals them to be in different stages of evolution at distinct ages, on the one hand, and in varied geodynamic contexts on the other. In other words, their distribution as well as their characteristics obey of twofold logic, geodynamic situational logic and historical logic. Now, now let's talk to main basin types. On consideration of their dominant mechanisms alone, the following four major classes of basin may be distinguished in the simplest manner. Rift-type basins in cratonic areas, stable R basins in continental areas, passive margins in pericratonic situations, and mobile basins in orogenic belts. It is important to insist on the very general character of this classification of entities as complex and varied as sedimentary basins. In particular, it is important to analyze carefully the geological characteristics of a basin to clarify its history and its degree of evolution before attempting to classify it. And let's talk about basins of the rift type in cratonic areas. These basins correspond to true continental fractures, often following an arcing movement. They also form the seat of a sudden and active subsidence in an area that previously displayed great stability. They are distinguished more specifically by distension force and negative vertical movements causing considerable subsidence, often acting along blistered faults rapid sedimentation capable of giving rise to undercompactation and shale diaperisms, especially in cases of large inflows. How deltaic basins. Generally high geothermal gradients often associated with volcanic occurrences. These basins correspond to rift valleys and classic gravens. They generally exhibit an elongated and triangular form and pronounced subsidence. Now, the characteristics of the stable area basins in continental regions, which the Paris Basin is a good example, and the simplest basins in a cratonic situation are generally filled by a single megasequence. In some cases, they may result partly from the formation of peripheral uplifts. They frequently appear to start with the formation of gravens. And the passive major margin basins or called pull-apart basins occur in a pericratonic situations. They are well known on the edge of the Atlantic and Indian Oceans, hence their alternative name of Atlantic margin basins. They display a highly dissymmetric profile and two clearly distinct sedimentary cycles, corresponding to the rifting and post-rifting periods. Instead, orogenic belt basins, the basin of this family situated in a particularly unstable area and often qualified as mobile are generally distinguished by a wide variety of types and by greater structural and very often stratigraphic complexity, since tectonically unstable zones are also very mobile during periods of deposition. A distinction may be drawn broadly between two chief groups. The first of all, basins with predominantly vertical or shear movements corresponding or more or less to turn or intermontane basin, or basins strongly marked by a convergent movements and consisting largely of basins of the myo-geosynclinal and of four-deep type, since geosynclinals usually show a tendency to occur more in the form of fault and eroded ranges than specific basins.
So, how is the geodynamic of sedimentary basins? As it is known, sedimentary basins form and evolve under direct control of tectonic process. It could be either compressional, extensional, or strike-slip motion. Sedimentary basins are clearly related to the Wilson cycles, as it starts with a stable craton that later, on the control of tectonic motions, became a rift that later will be a sediment deposition zone. That will be the juvenile and mature stage. And finally, in the decline stage, as it is shown, it is compressional margins emerge. For Perrodon in 1983, he schematized three successive stages involved in the series of transformations in the sedimentary basins: juvenile stage, mature stage, and final stage. For juvenile stage, it is characterized for a high subsidence that result in the flexure stage of the basement, as it seems in this graphic, the lithospheric flexural profile. Later, in the mature stage, the basin is more stable, and sedimentation is more homogeneous, consolidated, and mature. For the final stage, that will be the death of the basin, where compressional mechanisms emerge and folded and eroded the marginal areas of the basins. Meanwhile, the center of the basin is filled. As we can see in this picture, juvenile stage is a heterogeneous deposit. In the next stage, it became more stable and extends planarly. These filling stages generally favors the maturation of hydrocarbon source rocks. And finally, the margins are folded due to compression. In this graphic is shown cumulative subsidence versus time. For example, the Cordillera Miogeocline foreland basin in North America started almost 600 million years ago. Since then, it has a progressive accumulation of sediment and subsidence, except for 170 million years ago, where it is observed a disturbance that may be caused by tectonic process. And so it will be the other graphics of basins.
I will continue to talk about the topic sedimentary environment and mechanisms and their petroleum consequence. This topic have subtopics. The first subtopic is mechanisms of subsidence and their impact of petroleum geology. Subsidence mechanisms are fundamental to petroleum geology and occur on different time scales. These processes are organized around the deposition of sediments. Subsidence also allows the accumulation and transformation of sediments during the burial process. This process has two stages. The first stage, initial stage, is about the positional environments give rise to a variety of materials and components. And the second stage uh, is about the dynamics of sedimentary passing organisms that materials into a single architecture. Continue. The second topic is about characteristics and rates of certain sedimentary environments. The positional environments which determine lithological phases and stratigraphic characteristics are key to the petroleum properties of sediments. The energy of this environment is a fundamental criterion. These criteria are low energy environment, such as open marines, and generate rocks such as carbonates, marls, and salts. Confined environments produce rocks with organic matter and evaporate with light porosity and permeability. And finally, organic rich black shales form in basins with stagnant and stratified water, creating optional conditions for oil generation. Mineral transformation related to subsidence. The subsidence allows the accumulation and burial of sediments, which leads to physical and chemical transformation due to pressure and temperature. Compaction and chemical transformation are common in this process. Temperature is a key factor in this process. As the sediments are buried, the temperature increases, resulting in recrystallizations and chemical changes, especially in carbonates and evaporates. However, compaction is a irreversible process, usually beyond a certain depth. External physical parameters. The pressure expert is influenced on the compaction of the sediments, reducing their porosity, permeability, and water content, while increasing their density, resistivity, and speed of sound transmissions. Pressure and temperature can reveal anomalies in the subsurface, such, such as abnormal pressure anomalies. These overpressures can be caused by diagenetic or metamorphic transformations as well as insufficient compaction mechanisms. To continue, Andre explained about the action of temperature.
The action of temperature. Mineral transformation related to subsidence refers to the physical and chemical process that occur in the sediments as they are buried, as my colleague Eudesia said. As this happens, not only pressure but also temperatures increase as the sediments are buried deeper, which can lead to deterioration, decomposition, and recrystallization of minerals. The general effect of temperature is known to accelerate chemical reactions kinetics very substantially. Heat transfer by conduction in the air crust dq is roughly governed by Fourier's law. K is the thermal conductivity of the medium. S is the area crossed by the quantity of heat dq during time dt. The differential of E divided to the differential of C is the geothermal gradient. As you can see in the last slide, K is a parameter of the Fourier's law. So the thermal conductivity of the rocks depends on their lithological and petrophysical characteristics, and especially on their density. It is very high in salt rocks, medium in sandstone carbonates, and low in shelly series. The geothermal gradient results from the heat flows and the thermal conductivity of the rocks. Geothermal flows partly originate in rock radioactivity and to an equal extent in a deep subcrustal flow, which can be strongly amplified locally by the rise of basic magmas. The heat involved by certain chemical reactions and the conversion into heat to the mechanical energy of orogenic deformations. As we can see in the picture, the continental areas away from tectonic active zones have average geothermal gradients. As we can see, temperature increases quickly with depth at mid-ocean ridges, and temperature increases slowly with depth at subduction zones than in mid-ocean ridges. It is possible to observe and to measure certain properties of minerals or organic particles which have been affected by an elevation in temperature. and which have preserved this transformation as a recorder. One of these was the transformation of smectite into lite. Smectite is stabilized as the temperature rises above the usual range at the Earth's surface. The reaction progresses faster as the temperature is higher, so two factors can raise the temperature: a proper geothermal gradient or an intrusion of hydrothermal solution. In both cases, the transformation has its own characteristics, as the temperature is the gradient and the speed of the process are different. The smectite transformation is carried out in the vast majority of cases by means of interstratified phases. These phases are minerals with mixed laminates of the poor components. The elicitation reaction progresses through the transformation of smectite to illite. The progress of the reactions is measured by the percent of illite laminate present in the interlayer. Another one was the vitrinite reflectance. Vitrinite reflectance is seen in metamorphosed organic sediments and is a parameter used in petroleum geology to evaluate the thermal maturity of the sedimentary rocks. Thermal maturity refers to the degree of heating that sedimentary rocks has experienced over geological time. Vitrinite reflectance increases as the sedimentary rock is subjected to higher temperatures, indicating that the rock has reached a higher degree of thermal maturity. Why this happens? As vitrinite is heated in the earth during burial, it changes its reflective properties. So these changes are caused by increasing condensation of carbon rings structures in the coal matrix. Also, the chemical reactions uh, occurs faster at high temperatures. We can notice that the time can compensate this. So the time is a really important part. Uh, as we can see in the graph of variation of reflectance of the vitrinity temperature versus temperature and time, uh, we can notice that it requires higher temperatures in the younger series and lower in the older ones. So we can conclude that thermal maturity depends directly on the action of the time and temperature.
Now I am gonna talk about transformation mechanisms. So the first mechanism is the genesis, which is the sum of all physical, biochemical, and physical-chemical processes that change the sediments after its deposition but before its final lithification, which is the rock formation. At first, the sediment is very porous and water can flow freely within the pores. But as depth increases, interstitial space is reduced. As you can see here in the slides, well, the depth are gonna increase. So at 500 meters, there is loss of porosity and expulsion of water because a mineral rearrangement takes place. An example of this rearrangement is that the aluminum and ferrum that are in the upper portions, then in the lower portions, appear in the form of amorphous hydroxides, as you can see in this picture. Below a depth of 500 meters, temperature intervenes, components are redistributed, and water is enriched with calcium but depleted in sulfates and carbonates. Feldspars are also dissolved. Now, the other mechanism is katagenesis, in which temperature takes an important role. Also, clays are kept in a constant equilibrium with interstitial water. At a depth of 2,500 to 4,500 meters at temperatures around 100 Celsius degrees, smectite, which is a member of the phyllosilicates family, is converted into ordered mixed layer clay minerals. This transformation occurs with the elimination of pure water at the start and plays an important role in the primary migration of hydrocarbons. Then, at a depth of 4 to 6 kilometers at pressures of 1000 to 1150 bar and temperatures of 150 to 200 Celsius degrees, there is absence of fractures. Also, clay acts as an osmotic membrane, increasing the concentration of grains. And finally, the organic matter matures and converts into coal and oil, then into wet and dry gas, which is the methane. Finally, the Anki or metagenesis. The Anki is characterized by an elite crystallinity index of 4 millimeters. Metagenesis applies to series that have a Vitrinite reflectance equal or greater than 2%. This is the zone prior to the metamorphic area, which is characterized by the predominance of elite and chloride in place. Also, pressures are high enough to make rocks have a viscosity and a reflectance greater than 4. Here in this zone, only highly evolved organic matter, such as anthracite and methane, can be. Now, I'm going to analyze all of these three mechanisms that I mentioned before. So, as you can see, the one that has the higher parameters is the metagenesis because it has a higher degree of exposure to heat and pressure over geological time. It also has a higher thermal maturity and a higher level of organic metamorphism. And this can be because it occurs at a depth of 6 to 8 kilometers, which is the highest depth of all of the previous mechanisms. And also at these depths, the temperature and pressures are higher. Finally, the boreal anomalies. There is a delay in compaction that forms under compacted beds under abnormally high pressures. This can occur when there is a thick and rapid clay sedimentation and there is no detrital intercalations which usually act as drains. Also, the undercompacted shales can become hydrocarbon-source rocks, acting as a shield that delay the hydrocarbon genesis. And also, the interstitial and dianetic water can't escape as depth increases, which prevents the loss of porosity to occur. Also, the pressure that is exerted on the subsurface rocks is high due to the weight of overlying material, so that the pressure gradient increases up to 2 bar per 10 meters. Also, these shale undercompacted shales act as seal and thermal insulation. Finally, the shale diaparism, as you can see here in this picture, there is a rising fluid of overpressure sediment that cause mud volcanoes. So as you can see, well, it is caused by the accumulation of sediments above that deform them into a series of sedimentary faults and faults that can split at the surface to form the mud volcanoes that I previously mentioned. Okay, so that's it for the presentation. Here are the references that we used to make this exposition.